This project studies the control of single robotic arm. A single robotic arm consists of sensors, controllers, and actuators. The objective of this project aims to design a control system to regulate the movement of the robotic arm.
In this slide, I will explain the methodology used for modeling the robotic arm control system. We begin by developing a flow diagram which starts with a switch generating the input voltage VST processed by the computer into a control signal VINT, then adjusted by the controller using feedback VOUT to drive the DC motor. The DC motor which converts VET into torque to move the roller and robotic arm, ensuring precise motion via a feedback loop. For a clearer and more simplified representation, the flow diagram is shown in the image on the left, outlining the DC motors processed from input, including the applied voltage E and current I, to output, which includes torque T and the mechanical motion or rotation of the arm omega. On the right side, the circuit diagram of the DC motor is displayed. The torque generated by the DC motor at the rotor is directly proportional to the armature current, and this relationship is expressed in equation 1. By applying the Laplace transform, we derive the armature equation for the input voltage EAS as shown in the equation 2, which establishes the relationship between the armature current IA, the angular displacement theta m, and the back EMF constant KB. The system also includes mechanical loading through gears, which transfer torque to a robotic arm. Using the DC motor's characteristic, we calculate the total inertia and damping using equation 3 to derive equation 4. After performing all derivation, substitutions, and calculation using the motor's parameters and assumed values, we obtain the desired transfer function of the DC motor as in equation 5, which represents the relationship between angular speed and voltage. This methodology established the theoretical foundation for designing and analyzing the control system, leading to the results and performance evaluation in the next session.
DC motors involve equations such as those for torque, current, back electromotive force, and armature. The code for this transfer function is derived after substituting the known parameters. We can get the result based on the design requirement for the closed-loop system performance and the damping ratio. This we also got the result is S12 is equal to minus 0.2 plus minus J 0.21. In the study of the control system, root locus and the static error analysis of the grid K for the GS with a clean characteristic of the power zeros and the asymptote. The change of the K affects the system state stability. The composite system changes the open loop transfer function through ds, the power zeros, and the real x intersection of the asymptote change. Its steady state error constant Kp is omitted, and the steady state error ESS is 0, indicate good steady.
For my NURUL compensated controller design, the controller was designed to meet the desired performance characteristic, which percentage overshoot is 5% and the cycling time is 20 seconds. From desired overshoot, we get the damping ratio is 0.6901 and the natural frequency is 0.2898 radius per second. By substituting new overshoot percentage and cycling time into general equation of second order system, we get new transfer function. Then the desired complex pulse is gained at negative 0.2 plus minus 0.2098 G. Since angle saturation is not satisfied, the new desired pulse are not on the original root locus. Hence, the system needs to be compensated via cascade compensation. 0 of the compensated ZC was assumed at position S equals to 0.0908 on the real RC segment, which cancel out the existing put. Therefore, we get PC equals to 0.4. From the loop transfer function, we can determine K equals to 0.084. Then, step response is 30 in MATLAB. For compensator controller design using SISO tools, the blue line indicates the initial desired results. Damping ratio was set at 0.6901 and the settling time was set at 0.20 seconds, which represent in the black line. The step was completed for root locus with lead compensator using SISO tools.
Here we can see the comparison in parameters for uncompensated and compensated control system. Uncompensated has longer settling time at 82 seconds and excessive overshoot at 55%, which lead to instability. Therefore, a lead compensator was added to provide adjustment to the system and achieve desired performance at 5% overshoot and 20 seconds settling time. And from the results, the desired values were achieved after the system was compensated, which reflect the ability of the compensator to improve stability. And in the second table, we can see that the pole and zero for both manual and SISO 2 compensator are same at 0.4 and 0.0908, which to explain the high errors in K value, the value is different due to high precision of SISO tool and simplified system used in manually compensated calculation. Here is the schematic diagram of the closed loop transfer function, where we can see the compensator added has transfer function of S plus 0.0908 over S plus 0.4, while the plant transfer function is 0.0595 over S squared plus 0.0908S. Here, this schematic diagram allows us to simulate the system's step response, which verify the design compensator to meet the desired performance criteria, including a settling time of 20 seconds and overshoot of 5%.
In conclusion, the robotic arm control system was achieved with the system transfer function represented by TS and percent overshoot of 55.15%, settling time of 88.13 seconds, and steady state error of 1.526. Then, to meet the performance requirement of 5% overshoot, settling time of 20 seconds, a lead compensator was designed using manual tool with gain 195.97 and SISO tool with gain 1.411. That is all. Thank you.